Alright, continuing on from where we left off last time. I actually want to show a little bit about how this program actually runs in the simulator. And sort of also want to highlight some differences of the simulator versus what it actually looks like, how code actually runs on a processor. So, just going to delete that. Was a big one I used earlier for some testing purposes. So anyway, so I have the simulator set up here, so let's just go ahead and hit the debug right here. We'll go ahead and build, I believe rebuild this. Yeah, build successful, and then it's going to start the process of the simulator. So it's launching the simulator here. Alright, perfect. So we can see that user program is running, breakpoint hit at line 39, and then we can go to the variables. So like I said, I explained that we have the latches and the ports. Now we actually set the latch here to be a hex value of 58. So if we look at the latch, what do you know? The value is 58, and then you can actually expand this to be each bit of these 9. And you can see that 3, 4, and 6 are actually indeed set to 1, which is what you want. Now, why isn't port set to be the same thing? Well, there's two things I have to say about that. And one of them is, first, I don't entirely know. The second is that port is a lot more time dependent than the latches are. So it could be that, you know, due to the capacitance issue, for example, you know, since port reads the actual value, I believe, of it, that due to capacitance, it could be that it's still reading a digital no, even though it's actually been set via latch to be a digital yes, a digital 1. So now this is a simulator, though, so you shouldn't really have any issues with capacitance because it's simulating a chip, unless their simulator takes a lot of stuff into consideration. So at this point, I'm going to say I don't really know why this acts the way this does. But since the latch is being set, and that's really kind of what we wanted to do to set an LED anyway, I would say that we're probably pretty good here. So I would say this is functioning as we want it to function. So I'm going to go ahead and press this green button right here, the green play button. Not to be confused with this green button over here that's no longer illuminated over here. So we'll just press this, and then it's going to run this function right here. And let's see what our latch is. Our latch is still exactly where it is. So I'm going to pause it because I'm guessing that this is not doing what it's supposed to do. Alright, upon further research, I realized that lat clear works basically exactly the same way as latch set does. So it is a special function register again, and in that, so special function registers are interesting in the fact that they're not something that you find in traditional desktop mobile programming. And the reason is because you're actually directly interacting with a silicon routine on the chip that actually goes and does something. So, as opposed to, again, I mean, when you boot a Windows program or Linux or Apple or even on a phone, like an iPhone or an Android phone, you have a firmware, then you have a post, which takes you to either system on a chip or a motherboard that actually runs an operating system. So Android is an operating system. You know, iPhone has, you know, an operating system. Linux, Windows, Mac will have operating systems. This doesn't really have that. Instead, what you're really doing is you're interacting directly with certain functions on the silicon, and you're using these special function registers as a way to send and receive information from and to parts of silicon that you wouldn't, in a way that you don't do in Windows. In Windows, there's honestly very few things you can do You can read files, you can write files. You can, send files over the internet, you can output things to the screen, but you don't really have, if I say, well, I want to turn this bit right here blue, this on the screen, you can't really do that. That is extremely difficult to do, because you have to have a program that takes control of the window and, interacts with, Windows, Linux, Apple, whatever, at a very low level in order to draw and render things like that, which is sort of a large degree what like a gaming engine would do. Is it handles some of the difficult pieces of actually drawing things to the screen. And for example, I mean, a lot of the graphics cards actually, you don't really draw things specifically to the screen. They're actually really sort of in charge of the render itself, and that's something that a lot of people don't realize is when you get insanely great graphics in like a video game, that is actually programs that you are running on the graphics card itself. So usually those are shaders or something like that. So that is actually like your computer couldn't create that without the graphics card. So that's why having a good graphics card is really important, and why it makes a huge difference as far as what your game looks like. More than, I mean, obviously your CPU is important too, but really those shaders and the code that is actually running on the graphics card itself is why the graphics look so good. So basically, your CPU has a program with a graphics card that sort of deals with taking control of your screen, and then the graphics card has sort of the basics that is sent from the computer as far as like maybe where the players are on the screen or whatever your scene is, and then there's actually programs that are downloaded into the graphics card, like shaders and things like that, that actually run to actually display some of the finer details. So if you have a better graphics card, you'll actually get more details because the program can run faster. It can run in a more detailed mode, for example. It's sort of a similar thing to that, is that, Windows, you really don't have direct access to the screen. You only have access to files and doing certain things and displaying characters on the screen through the interface that they provide you. And with PIC, you are going directly to the silicon. So you're really using these special function registers as a way to communicate between your program and the outside world. And that's really kind of the reason that you use a PIC chip and you get into this, is that not for the sake of just programming, but for the sake of being able to interact with the outside world and do things. And that's why the GPIO pins are such a huge component of these chips, is because, I mean, that's really why people get these chips, is so that you can do things in the real world, either reading sensors or, controlling things, turning lights on and off, working motors, And, again, a lot of it can kind of go to robotics, but, I mean, think of a DVD player, it's like, in order for a DVD player to run, it has to have a motor that spins and a tray that opens and a sensor to know if the doors open or closed, and maybe a sensor for the speed, and then so there's all sorts of think of a microwave oven. It's like there could probably isn't, but there could conceivably be a chip that runs that, and it's like you've got buttons and you've got a display, so you got to be able to enter how many minutes you want to microwave your food for, and hit start and hit cancel and stop, and really that inner face piece and the screen display is a lot of what it does. And then there's going to be a turning on or turning off of the actual microwave generator component, and then the turntable in the bottom, turning that on, turning that off, maybe a light inside, turning that on, turning that off. So not a lot of input-output, but if you look at a modern-day microwave and think about the number of buttons that are on there, it's like, yeah, it's got a 0 through 9 keypad on it, plus start, plus clear, and then it's got all these other little things on there, too. They're, like a potato mode and a, dinner plate and popcorn mode and, defrost, and, and it has multiple screens of like, okay, defrost, how many pounds do you want? Okay, is it 2 pounds? Is it 1 pound? If you put in 1,500 pounds, it'll say, oh, that's too big. You can't defrost that here. So that's sort of what you're looking for in one of these microcontrollers, as far as how they're interacting. Is that that's sort of the level of code that we're building. Is it's in so many more devices. You know, between printers and microwave ovens, it's in, you know, your refrigerator. You know, there's so many devices that these PICs are used in. And anyway, to get back to things, these special function registers are the way that you really are attaching your code here to the outside world. So I'm not really surprised now that I think about this that in order to clear this register, you actually have to set a value to it. And the reason is because you wouldn't necessarily want to clear every single bit on the register every time. So you don't want to just call it and say clear them all when you can send it a value and have it clear only part of it. So I have absolutely no idea if this works, but we'll try it. So we're just going to build clean right here. And then we're going to start debugging. Build successful. Let's debug this then. So first thing I should do is launch, run my code, and then stop at this breakpoint right here. That's what we're looking for. Da-ding, that's what it did. So now we're going to go ahead and move it forward to the next one. And we can see here that 5.8 was still selected, and it looks like 5.8 is still selected. So looks like whatever I did here with the clear is actually not working. This says not recognized, but I'm not really sure why that would be. So I can try a few other values here and see maybe why it's not. Basically, FF is going to be your highest. It's going to be putting ones everywhere. So if you pull it back up your calculator, clear it out and just hit FF, you can see that's binary. So actually we need to do 3 Fs to make sure we clear all of these pins. So let's try that. And I think I can just hit debug because it's going to build the whole project again anyway. So build successful. Launching. All right, so variables are set. Let's run it, see if it does anything. There we go. So for some reason, it did clear them out that time. So I'm not sure exactly what the difference is. That doesn't really make a whole lot of sense to me. Why I would have to set all those to clear, but that worked. So let's just go ahead and assume. So basically, I can hit play here again. It'll come around to this breakpoint, and then 58 should be set. So pins 3, 4, and 6. There we go. And then I hit it again, and should be print 0, which it is. So you would think that the next step would be just going in here to customize and then selecting your microchip starter kit. So I don't actually have mine plugged in. Looks like it's still in there connected from maybe last time I had it plugged in. I'm going to plug it in for real. All right, you can hear the ding. Okay, there it is. So now it actually shows up. And it's something that I can actually select. So I hit OK. Now I'm going to build clean for debug on the main project. And it will build successful. And then I'm going to program device for debugging main project. So I'm going to go ahead and select that. Alright. So, failed to program device. So why would that be? So let's actually see if we can make and program this device this way. Failed successful. Failed to program device. Oh, no, that's from last time. Configuration memory, boot configuration. Program verify complete. Alright, so it says it's done. It says it should be running. But guess what? It is not running. So, this took me a very long time to figure out. The reason is because, I'm going to open these up right here, configuration settings. So, there are a number of configuration settings that are specific to each one of these chips. You can actually find this yourself in here, in this folder, so you can see it says Program Files Microchip X32, because obviously that's what we're using, 144 docs, and then go to config set. You can see that that's the path that I have. Going back on config set, and then finding the chip that you have. And this basically shows you what all of the configuration headers that you need are and how you set them for your specific chip. These are going to be different for every chip. So, well, I'm not going to say they're going to be different for every chip, but I'm going to say that they can be different for every chip. So it's really kind of good to know which one is doing what. And one of the things that I know that we're going to need to do for sure is we're going to have to set some things as far as the watchdog timer. So let's figure out what they call the watchdog timer. Watchdog timer enable. So watchdog timer disabled. So what we do is we take that, we put that here. So obviously that's not a full line. I actually have to go back up to the top and we have to say pragma config. So every one of these is going to be that. Pragma config. So watchdog timer off. Watchdog timer off. Alright, so let's see here. Ethernet enable. I don't think we need to do that. Input divider. System. TPL range. I think this is important because I believe this is the clock speed that we're going to be running at. So I'm just going to pick 8 to 16 megahertz. Clock time. So you can have internal oscillators and external oscillators in order to go clock chips. And basically, really the reason you would use an external is if you really wanted to, or if you needed precision in your timing, which for what we're doing doesn't matter. For something where you're really trying to do data input output, it can matter a lot. So for example, like USB, their clock cycle is plus or minus, I think it's 0.5%. Yeah, I think it's 0.5%, which is not within the range of what you can do with an internal clock. So if you're just putting LEDs on and off, or, whatever, that's fine. Or like a microwave or something like that. I mean, you're not trying to program this thing digitally. You're relying on humans, and humans are incredibly slow when you think about how fast these chips run. So it's really not really that big of a deal to do that. So the other thing that I know for sure that I need to look at is I need to enable debugging. Okay, background debugger enabled. So debugging on. So we'll turn that on. Let's see here. Trace features and CPU are enabled. I think that sounds like a good thing to have on. ECC configuration, don't really care, I don't think. Debug mode CPU access. Allow CPU access to all regions. Yeah, sure. think that's fine. Secondary oscillator stuff, I don't know if we have to necessarily disable that. Code protection doesn't really matter. I'm not sure we really care. User ID, there's a lot of stuff in here that maybe doesn't necessarily matter. You can see how far we had to go, though. So there's a lot of options you can set. So, system oscillator selection. You know, I'm to a certain degree out of my depths here on exactly what we need. So I'm going to see if we can actually just run this as is and see what it does. Keep looking over here, but you know, there's just a tremendous number of options as far as, you know, what you can set, and you know, I just really don't know what we really need. It seems like there's duplicates. I've watched how reliable it is. This is like the 4th time I've seen this. Yeah, so it's in there 8 times. So I'm not really sure why that is, why there's duplicates. So maybe this list isn't actually as long as I think it is. Maybe there's some sort of a gap here with the config alt or something. Maybe like changes pages. So I guess we could just try and figure out user ID and see how many times that shows up. So right here, so that's the first one, and then it goes to Ethernet. First one then goes to Ethernet. So looks like, you know, if you see here, I'm not really sure why it's duplicated so many times. But that's good, because honestly, it's kind of unmanageable otherwise. So let's see if we can program this device. See what it says. Cross our fingers, hopefully it works. Target device not ready. Check configuration settings. Common use for this is a failure or oscillators. So maybe we need to set an oscillator bit selection. I was wondering if maybe we need to do that. Let's use this one. So I think what I'm doing here is specifying the system PLL oscillator. I know what that is. This is USB PLL. I see PLL a lot. PLL multiply. So let's see if that one works. If not, I would say the primary is probably a safe choice. Again, having absolutely no idea what I'm talking about, but sure. So I guess a note on that. You can conceivably fry one of your projects if you connect things incorrectly, but in general, you're not going to be able to do that with that code. Obviously, you can, you know, if you like were to disable debugging or something like that, and then load that into your chip, sure, you can break your chip. But to a large degree, like, it's not all that risky for me to try these settings, because if the programming fails, you know, and basically all you do is just try something different until it succeeds. And that's sort of the nice thing about having a programmer in the difference there. So it doesn't look like that one worked, so I'm curious what a PC. Looks like that's not even in there. PG. Alright, let's try the primary oscillator instead. Maybe that'll work. So I did not have a lot of luck with the way I was going about doing it, with just sort of randomly setting some bits. So the break that I took here was a little bit longer than I was expecting, but I have actually managed to find a good configuration. And you can see it is actually running on the board that I have here, and I will actually insert a video of it running at the end here. But let me just stop this, and I will kind of show you what I did. So for one, made a few code changes here. For one thing, all the Pragma stuff I put at the top. So it's all going to be at the top as opposed to being below the include. I'm not sure it actually matters, but This is the way it was designed to run, so I just figured I would do it that way. So one of the things that I did do is we had this void delay here, which again is just a function that just loops and does nothing, just soaks up CPU cycles. And we had delay in here about a dozen times or so. So what I did is I actually changed this to be a for loop, basically just based on this for loop here, to run 20 times. And then I also have a new function called, instead of large delay, called huge delay. It actually runs 200 times, so it runs this delay code 100,000 times 200 times. So what is that? 20 million times that it's running this code, and you'll see how fast this blinks here. And if you look all the way up here, you'll see that the I'm really running at 5 to 10 megahertz is the range. Out of this, and again, I'm not sure, again, 100% what all of the things on here specifically do, but I do believe I'm running somewhere in that range, 5 to 10 megahertz, which is incredibly slow compared to the processors that we have today. You know, like an Intel or AMD off-the-shelf processor is going to run at, you know, 2.5 gigahertz or 3 gigahertz, 3.5 gigahertz, as opposed to 5 megahertz, so approximately 500 to 1,000 times faster than this, which is a lot, but not a lot considering the cost difference that you can really get off these chips. So I guess you could say that those chips are about 500 times more expensive, depending on which chip you get, compared to a PIC chip that's going to be running, you know, 5 or 10 megahertz versus, you know, the gigahertz. So I would say maybe it does actually scale fairly well. Anyway, I digress. So this does work, but I want to show you how I came up with these configuration bits here, and that is through this function in MPLAB X. So if you go to Window and then pick Memory Views, and then you go to Configuration Bits, this is where I went. And really what this is largely the manual that I showed you, the HTML manual. It really kind of shows you all of the options that you can select from, and it's a very simple, easy to use kind of thing that really kind of, you know, it just, you know, on, off, and basically the defaults that have loaded in here are acceptable defaults. So basically I didn't change anything. I just literally clicked generate source code to output, and literally it just dumps this out to the output. You just copy everything here. Well, you could just copy everything, and then you go back to your C file, and then everything from this include X up, you just overwrite it, just paste it over, and this is literally, like I said, this is a valid config now. So it has everything set that needs to be set. So you can, and it's also like very well, you know, I mean, think about how much time that would take to go through and, you know, set every one of those comments and line it up, and, you know, it's very time consuming. So it's really a great feature to have of MPLAB X to use this, because it doesn't really matter what your chip is. That's the thing, is this is the configuration for this chip. You know, if you had a different chip that you're running, basically you just change your device up here, and you're good to go. So you'd be running on whatever that chip is, and there are a lot of chips in there. I mean, I don't remember how many chips microchip. I don't know how many chips microchip makes, but I think it's over 2,000 chips they make. So anyway, so I just changed the compiler version there to 1.4. I changed it back to 1.44. I changed it back to 1.40. Just to see if maybe that was what was causing the load to fail. So one of the things you can actually see your version is right here. So it's actually a separate executable, it's called, that actually does the loading, or does the compilations, and you can see just sort of GCC standard, you know, kind of compiler terminology here, you know, and then I'm sure it has some sort of, you know, linker. Maybe it doesn't. I don't know exactly what is required for this. Looks like it's got an output here. I'm not sure what the outputs are that it creates. If it creates some sort of an object file, I think it does create an object file, and then it loads the object file in. I don't really think that there's any libraries that I'm using. So I'm not really sure why you would need to necessarily have the linker stage as much, but whatever. I'm not an expert by any means at that. I'm just happy to get this thing, little LEDs to flash. That makes me happy. So, you know, as I progress through, I'm sure I will learn more and more, and I will share it with you guys as far as you know, how these things function. So let's see here. Target halted. Let's see if it's halting on. That was old. So I don't actually have the breakpoints in here. I took them out. And the reason is because it appeared to be running. So, yep, this is definitely running as it is. So I'm actually going to shoot a short video here of this flashing. And I'll insert it at the end, and then I'm going to go back over the configuration bits in the next video. Alright, just wanted to show you these blinking LEDs here. This is the microchip Curiosity PIC32MZ development board with integrated debug headers. So this is currently plugged into my computer, running on non-debug mode, and basically you can see that this is the PIC micro controller right here is running. And you can see that LEDs are flashing away. Nothing else is really connected here. This is the wireless card. You can see based on the right here that you have that is the antenna, believe it or not. And they actually stick it outside of the board there because otherwise the some of the ground planes and stuff that are part of the circuit board will actually interfere with the wireless signal and make the wireless signal tremendously worse. So just sort of an overview. I don't have any of the daughter cards plugged in. We can plug one in here, and I think you can plug maybe external debugger in here. I don't know exactly what that one's for. And then obviously you can see here at the bottom that there's other GPIO pins that they've made. Oh, there's one debug header right there, the ICSP header. But you can see they actually have the USB debug is right there, but really, honestly, it's actually mostly on the back here. This is actually, it's upside down, but you can see this is actually the chip micro processor that's actually in charge of running debug and handling those commands. So it's obviously a USB enabled device and does all that and can handle, you know, master clear and all that kind of stuff that's associated with programming PIC chip. So anyway, so this is just a first example. I just wanted to show you that the LEDs are indeed flashing, and this is approximately the rate that they're flashing at. We're running somewhere between 5 and 10 megahertz here, and this is with a 20 million cycle if loop between flashes. So it turns on, runs 20 million cycles, turns off, runs 20 million cycles, then turns back on. So if you were to drop this down, it would be substantially faster. The first time I ran, I think we were running more like a couple 100,000, and you could it was basically on with a slight flutter. It was not what you would call blinking, just because it was going in such a fast clip. So I'm going to attach this then to my other video that has the code associated with this.